of alkynes. And if we remember alkenes, right, we had several ways to do that. We had water and acid. We had our mercury acetate followed by demercuration, right? And we had hydroboration oxidation. What we're going to see is something similar. We're going to see a couple of different ways to do this based on radiochemistry, but the product of the alkyne is not what we might expect. If we add water, acid, and a catalyst, and this catalyst is most necessary for terminal alkynes, but you'll see it used for several others. We'll cover halogenation today. We missed it in the last class. I put a problem, but we missed it. It's actually later in the chapter. So good question, Bruno. So if we look here, what we end up with is not the alcohol, but the ketone. And what's going here, and we'll look at the mechanism, is that the mercury is acting as a catalyst, but what we end up with in this first step is this species, which is known as an enol, but that enol will change to the ketone. These aren't resonance structures, these are tautomers of each other, and the ketone is more stable. Right? So we can create an enol. So if we think about it, that looks very much like what we're doing here. And not sure if anybody would have caught that, but I drew the wrong regiochemistry. This is the right regiochemistry. So we create that enol, and then that enol will tautomerize to the ketone, and the ketone is more stable. Mercury catalyzes this. For internals, you'll see textbooks that don't have the mercury added for internals. This textbook kind of simplifies it and says add mercury all the time. It's not necessary for internals, but it's a catalyst and it makes the reaction go slightly faster. The only downside is you're using mercury. If you were in a lab, you probably would try it without mercury first and see if the reaction occurred rapidly. So let's go ahead and look at the mechanism. So what we're adding is a mercury salt. So we can have that come in. That gives us our mercury. Right, but then our mercury can go to this, right? So we can ring open that. So that's going to be going back and forth. We've got two different resonance structures there. So that's how the catalyst works. And then when we look at the second step, now we've got our positive here. Now we add our water. We've got the lone pair. Lone pair comes in and attacks the carbocation. And then we get proton transfer. So proton transfer picks up this proton. It gets us to our mercury. Oh, don't forget my double bond. Right, Now I'm gonna start over here. So instead of turning the corner, I'm gonna start on a new line. Remember, we still have acid and water. So now we get a protonation. Add the proton in. And the electrons, oops, don't forget your positive. There's a positive there. Then this comes down to the positive. I know this is a long mechanism. And then at this point, we get loss of our mercury. Okay, so we got the positive, so the mercury is then lost. And this gets us to our enol. So the first thing that happens is you create the enol. So the mercury activates the triple bond, right? We get the, oh, I didn't mean to erase that. Anybody else feel my pain? Okay, so we need to put that back. So we have our mercury here. This is what I meant to do. So we get this, cycle it just like we would before, except that this one is a +2. And then we ring open that gives us a positive charge here. Water attacks that positive, that carbocation. We get a proton transfer here. Right, proton transfer giving us this species. Then this species, these are the same, right? So I could have gone around the corner. This picks up a proton, right? So we get a proton transfer. Now we're going to form a stabilized species here. So the oxygen is more stable than the empty orbital carbocation. But then at this point, we get the mercury to leave to give us the enol. The enols not are more stable, then we get tautomerization. So this is our enol keto okay. And the one I'm going to show you here is acid catalyzed. And we'll see one in a minute that's base catalyzed. So in the acid catalyzed, we start with the enol. Okay. That's going to pick up a proton. There's a couple of ways you could show this, but turns out that this reaction is the predominant change. So we picked up a proton there, right? And then we get a proton transfer. So it's acid catalyzed, we get a couple of proton transfers, picks up the proton there, giving us the neutral ketone. And the ketone form is just more stable than the enol, so this reaction, drives forward. Questions about this mechanism? Okay, if I was somebody that was going to study this mechanism, I would study the enol ketol tautomerization. several years ago, and it's been almost a decade now, so I'm not sure if this is still possible, but on the MCAT, they actually had an enol keto tautomerization. It is something you see quite often in biological systems. Sometimes it's an enol keto tautomerization, sometimes it's a nitrogen substituted, where you'd be going from an amine to, let's say, an imine, amine versus imine. They, in my Texan / Cajun dyslexic pronunciations, you do have some problems with me. So don't go to Harvard and say amine and imine, but when we get there, you'll understand they aren't pronounced that way, but I pronounce that way for clarity. Okay. All right. So this is the part of this this all here kind of explains how we get there. But if you were going to spend some time on it, I'd spend it on the enol, the ketone tautomerization. Now you can use the same reagents, and this textbook does use the same reagents for internal. So again, you know, water and acid are our main reagents. The mercury underneath the arrow is our catalyst. And the thing to remember here is that whenever you're dealing with this type of species, right, you don't have any selectivity, right? So you have, you know, 2 and 3, and here we have the 2 and 3 position. So we could add that to either side. So when it's terminal, you're going to have regioselectivity. When it is internal, you're not going to have regioselectivity. And if we look at the regioselectivity up here, right, this is a Markovnikov style addition, right? We're adding the OH to the more stable side. This is the more stable carbocation. Right, and so this is a Markovnikov. So regioselectivity for terminals is Marco style, but internals, we're going to get both products. Right? Okay, so that is acid and water with mercury. We don't have the same thing as oxymercuration, demercuration, because more or less as a catalyst, we're using the mercury, but we do have hydroboration oxidation. We're not going to go through the whole mechanism on this one, so your hands can take a break. But we do need to look at the base catalyzed tautomerization. So here, if we take this, right, BH3 THF, for a terminal, right, we'll end up with an aldehyde. We're not going to go through the full mechanism, but we do need to look at, notice here that our reagents are base now. So we're ending up with the aldehyde. The addition of the alcohol is actually going to form both the enol first, but then it's going to need to tautomerize to the aldehyde, right? So the tautomerization in this case can't be acid catalyzed. It's going to have to be base promoted. Okay, so base or base catalyzed. And on this case, let's use this one. We've got the OH terminal. So the boron is going to add anti-Markovnikov. Okay, so just with alkenes, the boron does anti-Markovnikov. So therefore, then this, what we have happening is our base comes in. We pull proton off, so we get a proton transfer. And the book shows this in 2 steps. I tend to like to show this in 1 step. Okay, this comes down, this pulls that proton, and we end up with our hydrogen. Okay, now convention, we tend to show aldehydes with this hydrogen, right? So this hydrogen is the way you normally show aldehyde. So up here, I didn't show that. That's correct, but by convention, showing the aldehyde is usually the trend. You'll see it both ways in publications, but I tend to show the hydrogen so that you're aware that it's an aldehyde. But if you see something like this in a homework set or in another book, that's also an aldehyde. Remember that you don't show hydrogens normally, but here the mechanism, we're showing that hydrogen. And then here, I didn't show it because I didn't show it over here, but convention, you do show the hydrogens like this. So this is base catalyzed tautomerization. Like the acid catalyzed tautomerization, if I was going to spend some time on some mechanisms on hydration of alkynes, I would learn the acid catalyzed and the base catalyzed tautomerizations. Be able to do both of those, and they're really just proton transfers, you know, with some rearrangements of electrons. Now, there is one concern with the use of the BH3, which is when we look at BH3, right, it can add twice to the alkyne, which complicates the reaction and actually will not get us to the product we desire, right? So the BH3 can add twice. It doesn't always add twice, it will add twice, but there are better reagents. Those 2 better reagents are bulky 1 hydrogen boron species. So here we have diacetyl amyl borane. And I may just start over there. Okay. And the other one, again, the idea is it only has 1 BH, right? So it's going to add once to an alkyne. Why would it add twice? Because the alkyne has 2 double bonds, right? So it can add twice. So here, if we look at this species, we can get this big species. The abbreviation is known as B9BBN, you know, kind of like 8 BBN, but 9BBN. So and you can see from the name why we call it 9BBN instead of saying 9-borobicyclo-331 nonane. It just makes more sense. Both of these are the preferred boranes that you would use for hydroboration of alkynes. Again, because it decreases the complications that we would see with BH3. BH3 will work. These are the preferred. Okay, and you'll see that in most of our textbooks, this is what they're going to use. Okay, so the regiochemistry here, again, this is the big difference between these 2. So if we look at our 2 possibilities, is that H2SO4 water and the mercury salt, right? That's going to give us a ketone. The diacetyl borane followed by hydrogen peroxide and base will give us the aldehyde. we get those two species, right? And then if we look at those two, the other thing we can look at is internals. And with internals, right, we don't have any selectivity. So whether we use water, an acid, and the mercury salt, or we add the, like 9 BBN, those are all interchangeable. What we're going to end up with is both products. So we have no regioselectivity on internals. When we had alkenes, we did, because alkenes could have another carbon. For an alkyne, they can only have one carbon added, right? So we can't have two. So the two sides of an alkyne are equivalent as far as their stability, because they're only going to have either one carbon internal. If it's terminal, right, you have the hydrogen, there is selectivity. Okay, got a question. What is the first better reagent for hydroboration? For alkanes, it's BH3 and THF. For alkynes, it's either diacetylenediamine or 9 BBN. So either of those are correct. So you can interchange those, right? So the preferred for alkynes is diacetylenediamine or 9 BBN. Either way is fine. And the shorthand that you'll see is the name diacetylenediamine or 9 BBN, like this. Okay. All right. Questions about hydrations, other questions about hydrations? Okay, halogenations. Okay, if we add an excess, we're going to get the tetrahalide. The mechanism is not well understood. Okay, so this one is one of those where we won't be looking at the mechanism. One equivalent is sometimes possible. Some of the older textbooks don't do one equivalent because it's problematic. And one of the problems with it is sometimes it doesn't work really well, meaning you end up with the tetrahalide anyway. But there are cases where it will work. But the interesting thing about where it will work is that, and again, this comes from not understanding the mechanism very well, we get the trans, which we would expect, are the anti-addition, but we also get the cis addition, which is somewhat unexpected. Okay, so you get both of these. This one is the major, and this one is the minor. Okay, so one equivalent is sometimes possible. If you see one equivalent, they're expecting you to show one of these two products. The trans is the major, but you can also get syn addition, right? So you get anti and syn addition. Remember, with alkenes, you only got the anti-addition. You never got the syn addition. And so this is a difference. And that's, the mechanism is complex. And there are still chemists that when they have a little time on the side, they're still working on this one. Here's another one where we're not going to look at the mechanisms. It's a little better understood than the other one, but it's still pretty complex, and there's a couple of deviations in it. Here, what we end up with is going from the alkyne to carboxylic acids. The big difference is here from the ozonolysis of alkenes. We still start with ozone, but then in the second step, remember that in alkenes, we added a reductive group, either dimethyl sulfide or some type of sodium sulfite. Here, we just add water. All we need is water to get to the carboxylic acid groups. And so the second step is just making it wet. If you don't really want a water solution because the water will absorb the ozone and complicate the reaction. So that's why it's a 1 and 2 step. If we look at the interesting thing about this is that we can also use this ozone, right, as a way to decrease our number of carbons. So if we look here, right, we have 1, 2, 3, 4, 5 carbons. But in here we have 2, 3, 4, 5, right? We've lost our carbon, so there's only 4 carbons here, right? We've lost the other carbon as CO2. So this is a method to actually, for terminal alkynes, you can even think internal alkynes, to change our carbon structure. So we're cleaving our carbon structure here. So like with ozonolysis of alkenes, the interesting thing with this one is for terminals, you can knock off 1 carbon. It actually turns out that losing a carbon is not an easy process, losing 1 carbon. Sometimes it's easier to lose 2 carbons than 1 carbon. Okay. Questions about ozonolysis? Again, not a very well understood mechanism. It does tend to go through an ozonide, but we're not going to focus on that. We already looked at this one, but now we need to really take a deep look at it because it turns out to be one of the most important reactions that we're going to need because it forms carbon-carbon bond forming, is alkylation of terminal alkynes. So here, what we can do is use the terminal alkynes to change our carbon structure. So we're going from 4 carbons right to 6 carbons. So I've actually changed my carbon structure. How this occurs, right? The first step is to lose that proton. So we get a proton transfer using the sodium amide as a base, so the NH2. So we get a proton abstraction. That gives me the terminal acetylide. You'll hear me say that quite a bit. Acetylide is talking about acetylene, but acetylide is the negative species. And then what we do is bring in our electrophile. Right, so now we have not the triple bond, right? But that negative carbon is my nucleophile, right? That carbon is my electrophile, and this is my good leaving group. So negative, negative attacks that electrophile, bromide leaves. Okay, we end up with this species, right? And that's our product. So this allows us to create longer carbon chains. We can also create if we think about this one, so this is a retro arrow, right? So what we're doing is we're going from 2 carbons to 3 carbon to 5 carbons. But in this one, right, let's look at where our triple bond is. So this is part of the analysis. It looks like I'm going to be breaking that bond. I'm going to be breaking that bond, right? So I'm going to be adding, I'm not just adding 3 carbons, I'm going to have to be adding 2 carbons and 1 carbon. Now, in this case, it's pretty obvious how we're going to have to do this. We're going to have to do one and the other, but it turns out that that is the case whenever we do this, because if we, here's the problem. If I have this and I try to add 2 equivalents of sodium NH2 to create this species, right? This is very unstable, right? So that's not going to occur, right? So whenever we're adding to both sides, what we have to do is start with one side and add our base, and I'll go ahead and draw it out in H2, right? So this gets our, forms our anion. And then we add one of our electrophiles, right? So we can add the iodide or bromide or chloride. And then that gives us this side. And then we add another equivalent. So step 3 here to give us the anion. And then we add our other electrophile to get us to the final product. Okay, questions about this one? So let's try some product reactions with this. And then we'll get into synthesis. Let's take some time to put the reagents down on these. Okay, let's go ahead and take a look. This first one, right? We need to make the acetylide, so sodium amide followed by, we need this group, right? So this turns out to be on that second position. And we'd use the bromide or iodide, so several different possibilities here. And then here, right, we're adding to this. The nice thing is this one is symmetric. Right, so since it's symmetric, we're only going to end up with one product. So we could do water, acid, and mercury sulfate, right? Or it would have been just as fine to use the diisoamyl borane and the hydrogen peroxide and base. Okay, in this case, it's internal. Either of these would have given us the same product because the starting material is symmetric, right? No matter where I add the first alcohol to form the enol that then becomes the ketone, I'll end up with the same product. And the last one here, right, again, we're going to form the acetylide, and we need just to add the R group with a good leaving group to get us to our product. The last section in this chapter is synthetic strategies. So let's look at a few potential possibilities here. So let's see if we can make so on this one, this synthetic strategy, what we're looking at is adding some carbons. So we're going to add those carbons in a way to form the functional group. So what I'd be watching for here is the location of my functional group. Right, I would also notice that I'm going to 5 carbons. Here I'm starting with 2 carbons. I know that I can take this species, right, and add R group, and I can take that and add another R group, and I'll put R prime here. Here, right, I have a double bond, but I'm going to have to add my R groups before I reduce the double bond because there is no carbon-carbon bond forming reaction for alkenes. And then I should be able to take this to that, right, with a reduction. So notice here what I've done for my strategic strategy, right? I've tried to point out a few things here. I've tried to think about, okay, I've got 5 carbons. That means I'm gonna have to add carbons. That means I need a carbon bond forming reaction, carbon to carbon bond forming reaction. I've got a functional group in the 2nd and 3rd position, right? So I'm gonna have to consider that. But then whenever I started drawing this out, right, I didn't put any reagents. I just thought about what I'm gonna have to do. If this is in a 2-3 position and that looks non-symmetric, right, this group and that group are not the same, then I'm gonna have to add 1 R group and add a different R group to get my carbon skeleton, right? By this point, I want my carbon skeleton right. And then this carbon skeleton, well, I should be able to reduce a triple bond to a double bond. I did all of this without worrying about reagents. Okay, this is one of the things you need to think about when you're doing strategies. Know what is possible, right? You know that by working problems and doing things. We know that an alkene, right, could I have taken and started with, let's put in a different group, right? So let's say that we started here and the first thing we did was go to that. Could we then have gone to this and that, right? Well, the first step is okay, right? This step is okay, but we don't have a reaction for that, and we don't have a reaction for this. Okay, so you need to think about these processes, and before you start worrying about your reagents, think about whether something is viable or not. Okay, once we have this drawn out, that's when we can start thinking about the reagents, and we flip it around, and I don't want to use purple there, so let's use the blue. Okay, so the first thing we're going to do is, add this group, right? And then right now this gives us our carbon skeleton, right? So we've added 2 carbons to one side, 1 to the other. We have our functional group in the right position, in that 2 to 3 position. Okay, and so then at this point we need to go to the trans. Right? And how do we do the trans? That was on Monday, right? We used dissolving metal, which is sodium in ammonia, not sodium amide, but sodium in ammonia, and that'll give us our trans position. Questions about this synthetic strategy? Okay. Let's try another one. This one, I'll give you a little time to think about it. Okay. Think about how we could do this one. Okay, we have a question. The starting material is missing a pi bond. Is that the question? No, it's not. I meant for it to be an alkene. But that's a good catch. You currently do not know a way to take an alkene to an aldehyde. So the question actually points out something that we need to know. First is, to get to this, the only way I know how to do that right now is from this species, right? And so therefore I need to think about, how do I get from here to there? And I could get there from there to here by going through a dibromide, right? So to do this, I need to convert my alkene to an alkyne so that I can do the terminal hydroboration oxidation to get the aldehyde. Now, later when we get to alcohols, you'll see another way to do this, right? So there'll be a different path to do this. But currently, as the question pointed out, I need an alkyne. Well, I need to make that alkyne. And that's one of the synthetic strategies. So here's what I'm going to have to do that, right? I'm going to take my double bond. I'm going to react that with bromine in a non-aqueous solvent. That'll end up giving me the dibromide, right? And then I know if y'all are like me and OCD, it always drives me nuts to have the 2 bromines on the same side. So it is anti-addition. And so then here, right, we're going to add a large excess of our base. That's going to get me to this species. Remember, the sodium amide can deprotonate a terminal. So then I'm going to need to add water. So usually you see that as a 1 and 2 step, right? That gets me to the water. And then now I've got my alkyne with, 9 BBN or diacylamyl borane, followed by the hydrogen peroxide base. It can get us to our aldehyde. Okay. Questions about this one? All right, let's do one more. We got a couple minutes. In the last one, we had one where we knew we needed an alkyne to end up with the aldehyde. Here, right, we're going to need to have an alkene. We also know we're going to need to add 2 carbons, right? So we got to add 2 carbons. Then we're going to have to turn that alkyne into an alkene so that we can get the alcohol. If we try to do it from the alkyne, right, we're going to end up with the aldehyde. Okay, so therefore, and again, we're trying to give you one more kind of opportunity here, but running out of time. So first one, right, we use our sodium amide. So we make the acetylide, we re-add our carbon group, right, and it could be iodide, bromide, chloride. We just need a good leaving group on our correct number of carbons. Then we want to reduce this. We can use any of our either our dissolving metal or our Lindlar's catalyst. Because I've done both of these reactions, I'm going to pick the Lindlar's catalyst because it's simpler. You just filter out the Lindlar's catalyst, you have the product. And then here we do BH3 THF, right, followed by our hydrogen peroxide and base. Oh, I didn't give myself enough room there. And that will get me to the anti-Markovnikov addition of the alcohol. Okay. All right. Well, that is the end of chapter 9. So we're going to start chapter 10, radicals, on Friday. It'll probably take 2 days, maybe, to do chapter 10. It's